All right, I think we should be connected. Let's go and check. And assuming we are, we're going to stand by for just a minute while we wait for people and set up a few more things.
Sure.
But we should be live now. So I'm going to do is I'm going to put it to the standby window while we get that set up.
Yeah, I see a video feed on YouTube.
Great. So I will leave it like that for just a second then. All right. So you see which thing? Did it?
Sure. Standbys on YouTube. There
Okay.
definitely is a lag as expected, so just
Yeah,
note that.
it just was doing kind of weird things, but okay. It is sharing just the live feed. Okay. If that is good.
Standby is on YouTube, the standby screen.
Okay, great. So I'm just going to say live now. Oop. Right. It's off 6 o'clock. All right. I think that is good for my side then. We have the stream set up, and I think I have most props ready. Grab this. All right. I'm ready if you are.
Yes, I am. You can hear me
All right.
clearly?
Yes, I can. All right.
Perfect.
Let's get to it then. I guess I can start if that's all good. Hi, I'm John McMaster here in my Silicon Valley garage slash lair.
Hey, and I'm Yusuf, and we are happy to be back after a long, long hiatus.
Welcome to Geek Moniker.
Yeah.
What do we have today, Yusuf?
Okay, so this is cool. Okay, this is why I wanted this video because it's something you do not expect. It's looking under the surface using IR. It's something you think, X-rays can do, but it's pretty impressive the images you get with IR only.
Sure. And to give some background, part of some of the reasons why we might do this is the first is that sometimes you want to look at a chip and understand, like, hey, what's the transistor layer of this chip? Instead of looking at, say, the top metal layer with all the power routing, you can't see the transistors because all the metal layers for power routing are obscuring all the interesting logic underneath. So one option is you can use harsh chemicals like hydrofluoric acid or do some very high touch processes like lapping to remove the layers of the chip to see the transistors below. But another option is you flip over the chip, and instead of looking at the front side that most people are used to looking at, at least what you've typically seen for a die shot. Instead, you flip it over and you use infrared light to look through essentially the silicon wafer, which usually looks opaque. Just to grab one as a reference here, I have no idea what this wafer is. Typically you would look at this side and you see all the circuitry here. Instead, we're flipping it over and we're going to look through this side, which to you and me, we can't see anything. But if we go to, say, 1060 nanometers, we can actually see this through a little bit, although a little bit difficult. So that's what we're going to explore today, is what can we do with that? All right. So with that, then, unless you have any questions about that, maybe I could bring up a microscope and just show some examples about kind of the processes I've used over time and, the directions I see this going.
Yeah, definitely. Let's get into some images, and then I do have a couple of questions.
Sounds good. And then the other thing I'll add while I'm preparing this, another reason you might do this is if you have, so let's say a tool that you want to locate on the chip, you also can use this to look through the backside and figure out where you are, which sometimes is useful, for example, for certain security applications. So what I'm using over here is what we call one of our Labsmore imaging platform microscopes. This is kind of an internal slash prototype version we're calling our LIP-M2. It's very similar to our X1 microscope, if you've ever seen that on our website. But anyways, and I fitted up with a few different infrared illuminators, and we're going to go through those and kind of show what the evolution is and why you might use one versus the other. The first one, if I'm able to reach over, I'm going to put this in front of the camera just so we have a visual reference, is we're going to use what was kind of the naive solution when I got started, which was, hey, let's use the infrared rated objectives with as much infrared light as possible. So I think a first question I'm going to ask, so we have 24 1060 nanometer LEDs. Yusuf, what would you say a typical LED costs? Like if you wanted a 5mm ballpark, not
Like
not looking
5 cents, 10 cents.
Yeah, certainly in that ballpark, in the order of cents. What if
Oh,
I
real
told you?
quick, let me
Yeah,
interject. It's a little
yeah.
hard to see you right now because we got the
Oh,
pyuscope screen up.
oh yeah.
Yeah, so if
So maybe do that, get back this. Okay. So we
yes,
we can see this right here. So this is a custom illuminator I built. So yeah, so typical LED is, let's say, 1 to 10 cents. Let's say somewhere in that range.
sure.
What if I told you that each of these LEDs was $10 each? So you're
Wow.
looking at about $250 worth of parts right here to build this. So and it only gets worse from there because you may be aware, like, these microscopes use these Mitutoyo objectives, which can get pretty spendy. This one, for example, is a BOM cost of essentially, an order of thousands of dollars right here. I think it's close to $2,000. But if you want to do infrared, they're very light sensitive. So, you might use these special rated, it's a little hard to see, I guess, with the glare, but these special rated infrared ones that capture a little bit more light. So by the time you total everything up in the setup, it starts really getting up there in the cost. Especially if you also use the recommended cameras for the setup, which we might talk a little bit later. This can get a little spendy, let's call it, as you
Right.
put this all together. But
Um,
yeah, let's start with that though. But
a quick question. So these
yeah.
IR LEDs are not the same ones you find in like your TV remote, right? These are like
Oh,
special wavelengths.
correct. Yeah, I guess I should clarify that. Is that a lot of those that are in the IR for remotes, they might be 800, 900 nanometers. Those are not so expensive. I don't know what they cost, but they're much more mass produced. These are such a longer wavelength that's why they're a more specialty item. And I'm not sure that they're so much inherently expensive as there's just not so much demand for these that they become expensive due to their specialized nature. Great question there. Okay, so I think without further ado, then I'm going to try to get pyuscope back on the screen here, and let's show what this looks like. Okay, so here is microscope software. And what I'm going to do to start with is I'm just going to put this on, visible light illumination. So let's just show you what does it look like as we just try to look with a normal microscope. And what we're expecting to see is basically just a solid silver back of the die, not a lot of features. So I'm going to focus on this. Oh, okay, there we go. Great. Okay, so and you see I don't have everything exactly flat, but that's fine for this video. But not a lot going on there, right? Like you're
Right.
really just looking at it, almost like if you just looked at a steel plate, it's very opaque. Let's turn on some magic now. So have this in the back of your mind. I'm gonna turn off the visible light, so it'll go a little bit dark. And I'm going to crank up our infrared ring illuminator. And the first thing I want to note here is that I've cranked that up to max. We don't really see anything. We've gone, this setup does not use a specialty infrared camera, so it's not super sensitive to infrared light. To work around that, we're going to start cranking up the gain of this camera so that, things start showing up. And now you see, wow, this image looks a little different. Ooh, maybe a little too much there. Maybe not a huge amount of detail yet, but at least we can see an image. And let's see if we can tune this a little bit. And I think we should be able to. Here we go. And you can see some circuitry over here. And maybe we could pop that back so we can get a better A/B comparison. But you can see now, can you see my mouse pointer?
I can, yes.
Great,
So
yeah.
they're
So you can
kind
see
of like ghosty looking features right there.
that's right. And I should say this is an RP2040, by the way, just for reference. That's what we're looking at right here.
And that's the Raspberry Pi 5 chip, right?
Not Raspberry Pi 5. This is kind of like a high performance microcontroller, I would say.
Okay.
So basically, if you're like Arduino on steroids, like what would an Arduino be like if you added like DMA and other stuff like that you normally think of on a higher end chip?
Sure.
Anyways, so let me just for completion, I'm going to turn back on the other illuminator just so you can just very clearly see what it looks like on the back of the chip. So you see now I go up and that's what we're looking through. So
Yeah.
you can see we go from absolutely no detail to some reasonable stuff. So let's pop that back over, and I'm going to focus down just so we get that back. And there we go. So you have to focus down a bit. So you can see something, but the picture is a bit fuzzy. And so let's talk a little bit about why that is. If you go up here, you can see there is a lot of stuff going on up here. Anytime you get an optical boundary, the light's going to scatter. And so we've got a poor quality light source essentially scattering off of all of this. Then you're going through the silicon, which is a diffuse material, and it just gets worse and worse the thicker the chip gets because things scatter a little bit more and more. Does that make sense?
Yes.
Yeah. So we don't get nearly the same quality, even using this same relatively nice setup, as we would expect to see if we had flipped the chip over and kind of looked at the equivalent circuitry. So if I present you with that, what do you think we might be able to do then to improve this image with that in mind?
I guess if it's scattering and that's what's causing it, maybe like directional light.
Directional light. Perfect. So that's one of the things. Let's start with that. Now, the other thing that we can do, although we're not going to do today, is if we also were to lap the surface of the chip flat, that would also help. Because if we said, hey, get rid of all the scratch marks and the dust and all of that, that'll also significantly improve that. So with that in mind, we're going to switch. Let me see. I think to improve the flow, I'm going to just bring up the image, and then afterwards we can take a look at what this physically looks like. But I'm going to switch now from the very expensive setup, which is, $250 illuminator plus, I don't know how much that objective is, over $2,000 new. Now we're going to switch to a very low cost objective, relatively speaking. I think this objective, maybe $50, and then 2 LEDs. And instead of being in a big ring, though, like they were before, now they're just going to be 180 degrees apart. So I'm going to focus down because this is at a very different focal distance. And I just want to check in. I don't know. I'm not watching the comments. If there's anybody with any questions on the stream.
So not a question, but Thermal World
Yeah.
21 says for IR, you can use a big IR heat lamp and put a very thin piece of silicon on the front of the microscope lens to filter what gets inside the lens and the camera.
Yes, you can. I have some concerns that it would have similar scattering problems to this, but I'm open to explore that
Sure.
for sure.
And maybe at the end of this talk, we can go back to it because I do have a question about his comment.
Sure, yeah, okay.
Yeah.
And so now what I'm going to try to do is line this up to start off on the absolute worst configuration. Okay, so now we're in the same location on the chip, or very roughly, but now we're using the non-long working distance achromatic objective that's just, kind of your bog standard objective, I would say. And similar image now. Let's see what it looks like now as we start going through this setup. So I'm going to turn off the lamp like we did before for the visible light. And we're going to do the same process where we have to crank up to see what we can see. And I'm going to crank this up a little bit. And actually, this doesn't look as bad as I was expecting it to. Let me see if I can actually make this work. Because I want to demonstrate the night and day ideally. Let's see if I can do this. How does that look? I think we're making it better. Let's see. It's a little bit of a finicky setup in some ways. So just bear with me. Now I was expecting to see it get really bright as everything scatters. Okay, there. I think we're at least in the ballpark of what I was trying to demonstrate. Let's see if we can get this. Okay, so this is at least in the ballpark. So I was trying to show is that I think this might be as good as we're going to get, is basically if you scatter the light and basically in the absolute worst direction, so 90 degrees relative to the grain of that cut, you're just going to get a terrible image. You can see now, because we've oriented this to only illuminate 90 degrees against that cut, it's just scattering light like crazy. And, even if we focus down, you really can't work anything out because we're just flooded with all this scattered light. And we've already lost the punchline a little bit because you saw it a little bit of nicer. But if we start rotating this, you see that with the different illumination angles, that scattering just starts to really disappear. And you see now the image is changing drastically.
Right.
And then I can boost this gain up a little bit more. And we start focusing down, and now we start seeing a much nicer image. Now it's still degraded from some of the stuff in the way, but compared to before, it's significantly improved. And if I were to tune this a little bit more, we might even be able to get a nicer image. Let's see if I can do that. Looks like that makes it worse. Then
I think that's nice.
Oh, do you see that one?
Yeah, this looks like you can see more features.
Yeah, I was trying to see. I think there's one that's a little higher contrast, but maybe that's the best we're going to get right now. Oops, while we're still on this stream here. So maybe we'll call that a win for now. Oops, and I think I knocked it out of the way. But anyways, you can imagine though, with a little bit of tuning, if you get both the focus right and the angle, you can get a much nicer image here. And I think maybe I should have cleaned this a little bit before, so we got a little bit of a sharper with this. But with a tuned, cleaned dye, you'll get something quite nice. And maybe I will even try to switch to another one that I know is a little bit sharper to give us a little better contrast.
Sure. And as you're doing
Yeah.
that, I had a question. So
Yes.
it doesn't feel like the image is the end product that people are looking for because it's going to be kind of blurry, kind of fuzzy, right? I assume, like you said, they're using these images for a function, right? Like locating a tool or instrument on a specific area of the die.
Yeah, I mean, it depends on the particular project. If it's a project where they want to image a very large process technology chip, maybe this is enough. For example, there was a proposal for us to do this with a 386 chip and with a cleaner back, a higher resolution objective, you might be able to actually get all of the detail. Or if you thin the chip, because also the thinner you make it, you'll also get a nicer image. But what a lot of the people that I know are interested in this are doing is they're using it to so-called floor plan the chip. They don't actually want to see the individual transistors. They just want to get an overview of what's going on. And this could be to quickly triage the chip to understand, like, hey, how much of the die area was allocated to SRAM, for example? That might be a question you could answer. Or if you have a tool like a fault injection laser, or maybe you have a EM probe, or maybe an EM fault injection device, you can use this to figure out where you are on the chip, and then that allows you to move that tool into position now that you can actually see through where that tool is located.
Very cool. And, you know, I guess we'll cover this a little later, but that's one of the features on one of our scopes, right? Being able to
Sure.
pair the IR imagery and tool attachments.
And so I'm going to try to do is tune this a little bit. Now you can see actually on this chip, I think the difference between the two modes where it's fully infrared opaque versus reflecting is almost a little more severe. It
Oh,
actually gives
that's
a
a
much
nice
nicer.
image. Yes.
Yeah, yeah. So I think the other one wasn't really, maybe it got a little bit dirty, unfortunately, before the stream. I'm just going to software zoom in a little bit so we can see what's
Sure.
going on. But yeah, you can imagine with even a higher resolution, because now we're actually not too far away from the transistor level, I think, on this one. And for reference, I believe this is a Xilinx Cool Runner 2 CPLD. So I think you're looking at kind of some of um, the basically the address routing or something like that are those big white
Okay.
blocks.
And is silicon the only material that IR penetrates, or can you see through like other uh,
Yeah,
materials?
so I don't have this handy, but recently I was doing a project understanding how LEDs are made. So I was looking at, for example, different RGB LED modules. And one of the issue was some of the epoxies that were used on these modules were cloudy, I think to intentionally sort of diffuse the LED light. And that allowed me to not see where the LEDs were within the modules. By using this 1060 nanometer light, though, I was able to pierce through that epoxy with all the bubbles, and I was able to locate the dyes within the module. So yes, it opens up a lot of possibilities where you might be able to see something that you really didn't think it would even be possible without opening it up.
Yeah. Very cool.
Yeah.
Oh, and Recession says counterfeit chip detection too.
You
Yes.
could do that. The issue is, some chips. So I have one that we could put on if we wanted to. So this is an NVIDIA Tegra, for example, and you can see there's the die exposed on the back. If you have a chip like this, you can look at it without decapping it. A lot of chips, though, won't have the silicon exposed without doing a little bit of sanding or something, like it might not require nitric acid. Unfortunately, at that point, I think the question is, like, if you wanted to do this non-invasively, would you want to put that chip back on your PCB after you sanded it, even if it didn't actually damage the chip necessarily as part of that process? So that would be my only question there, is depending what you're looking for, it could be a little bit shaky.
Very cool. Um, Anything else on this IR front from your side?
Yeah, I guess I would add one other thing is if you have a more sensitive camera, so what some people will use is they might use something like an in-gas camera, for example, is the classic way to do this, that is more sensitive to longer wavelengths. You also can use something like a 1200 nanometer LED source, and that's going to scatter less on that bulk silicon and get you clearer images. So you might have to do something like a longer integration time because the LEDs are not as powerful, the camera is not as sensitive. But if you're a little bit more patient, you'll get higher quality results.
And like, how far in the wavelengths can you go? Like, if it gets better and better.
Well, one of the issues is as you increase the wavelength, the resolution starts going down. You know, the wavelength, the resolution that you can get is limited to something like, lambda divided by, 2. Let's call it, and some factors for the objectives. Um, so even if you have a very nice objective with a numerical aperture close to 1, um, you're as you start increasing that lambda, if you went from say like 400 nanometers, which is, like low end of visible light, let's say you like, oh, I want to use 4,000 nanometer light, 4 micrometers. Even if your camera supports it, you've now hit your resolution by a factor of 10. And so since information is a squared function, because you have an X and a Y axis, you've actually incurred 100 times loss in data that you're capturing from that
Okay.
snapshot. So that loss can be quite significant if you don't really keep track of it.
Okay. So it is a balancing game there.
That's right. That's right. And you also get these challenges of, can you find a source for the wavelength you want? Can you get optics that have been designed for that? Because once you start going out, now those become very special bespoke parts. Maybe the military uses that for, some special, tank imager, but you're going to have a much harder time on buying that on, DigiKey, Amazon, something like that.
Sure.
Yeah. So I think that may be a good stopping point for today, then, to keep it short and sweet, unless you have any closing thoughts there.
No, I think that's good. Like it was pretty amazing, especially if you see the two images side by side. It's like really a stark difference between,
Yeah, we can.
what you see under visible and what you see under like IR.
Yeah, and there's one last glimpse there to emphasize that. Um, and if we're being really fancy, maybe we can get half and half. Let's see, does that work? I don't know. Anyways, kind of. You can kind of see it. Let's see if we turn up the gain there. There you go.
Mm.
Very cool. All right. Well, I think that's good. Unless there's any more questions, I would say we call it here.
Okay. Thank you everybody for tuning in, and we hope to have a lot more of these coming your way. So stay tuned.
Stay tuned, everyone. Take care. See you next time. Bye bye.
Bye.